Hi everyone, I'm Sarah. I'm from the University of Sydney in Australia, and I'm here to talk to you about my last two PhD projects, which have been my babies for the past couple of years. Okay. And before I start, I'd just like to acknowledge that this is in collaboration with my supervisor, Associate Professor John Ormerod, and give thanks to my research group in Sydney as well as the research group in Monash for very useful input into how the packages should look. And a very big thanks to Emi Tanaka for this slide design. So today I'm talking about discriminant analysis, and unless you've done a statistics course, you might not know what exactly it is. So discriminant analysis is one of the oldest classification methods that have been used in statistics, and essentially what it does is it assumes that your data is multivariate normal, and suppose you've got three classes, you'll try and model your data by three multivariate normals, and then for a new data point, you then assign it to the class that has the highest likelihood under one of those three multivariate normals. But the key thing is that it has a strict assumption of multivariate normality. And it's still used sometimes today, and it's available in the mass package through LDA and QDA. And so this is an example of what multivariate normal data that could be modeled by discriminant analysis would look like. However, it was suitable for data that was available at the time of Fisher. However, now, these days, we see data that comes in many different forms. So, for example, we have big, wide data that was in genomics that was described before. So you can imagine we have many thousands of features, but only a very few amount of samples. And it doesn't work. I'm not going to go into mathematics, but you have to take a matrix inverse, which doesn't work in this particular case. And our solution to this is a method called multiDA. And it also doesn't work for non-Gaussian response. So we have a strict multivariate normal assumption. So if you've got any mixture, or anything that's not even normal, or a mixture of normal and count or binary, it won't work there either. So we've also proposed a generalized DA or genDA algorithm to handle this type of data. So first, I'll introduce the multiDA package. And I'm going to motivate it by a particular data set. So we've got this small round blue cell tumor. I'm not a biologist, I might have pronounced it wrong. And this data set is pretty old that looks at classifying 4 different classes of childhood tumors that share very similar histology visually, but genetically they are quite different. So they're trying to build an algorithm that can be more accurate in assigning treatments to children. And it contains 83 microarray samples with nearly 1,600 genes, so it's quite wide, and it's not even the widest that we see in bioinformatics. But how can we use DA now to find important features and classify new samples for their cancer type if we can't, this is too wide for normal DA? And what we're going to first do is define what a discriminative feature is. We're going to estimate the properties of these features and then use this to predict a new cancer type. So first I'm going to give an example with 3 classes because the 4 classes is too many examples. So suppose I had 3 classes to model. If we assume we're going to make the big assumption that the features are independent, that's just due to the fact that the data is so wide, we can then ask ourselves, how can I group the features by class in each feature? So the first option we have is that there is no separate grouping, that they all act the same way. And so this is a null feature or not a discriminative feature at all. We can also model them by 2 groups. So we have one against the rest kind of features. So we could have groups 2 and 3 grouped together against class 1. We could have groups 1 and 3 grouped together against class 2. Or we could have groups 1 and 2 grouped together against class 3. So there's 3 separate ways you can group the features 2 ways. And then finally, we have it where all the classes are different for a particular feature. And so this is the most discriminative most unique type of way. So altogether, for a particular feature, if I've got 3 classes, there are 5 separate ways I could group the data together, and 4 of them out of the 5 are discriminative. They have some information about how the classes separate. And what our method does is that it uses a penalized likelihood ratio test to estimate the best fit for each feature. So we compare the likelihood of our fits for each. So in this case, we've got 5 groupings against, or 4 discriminative groupings against the null, and see which one's the most likely in this particular case. And then we use this information, I'm not going to go into the mathematics, to then use this to predict for a new class. But this is an R talk, no statistics talk, so I just thought to show you how the syntax actually works in the package. So it's called multi-DA because we are looking at a multiple hypothesis test kind of situation. So we've got many features, so we've got thousands of features, so hypothesis tests for discrimination across each feature. And they've also got multiple hypothesis tests within each feature to see which grouping is the most likely. So in this case, we have, we're going to input in a vector of class values, the actual groupings for training. And X stores our predictor space, so for example, the gene expression. The rows are the sample observations and the columns are the features. Now the penalty is called the extended BIC. This allows us to get consistency for large feature spaces. And so it penalizes not only on the number of groupings, number of features, like number of ways we could group the classes, but also number of features that we have. So it's more consistent for type 1 errors in this particular case. However, we also include the BIC penalty as an option if you want to minimize type 2 errors. Equal variance, so we do allow for the normal distributions being compared. If you want to have the group variances being set to be equal, this is an LDA type algorithm, or different, so it's a QDA type algorithm. And now we have uniquely is the set options part, which determines how many groupings we want to consider. So for example, for 3 classes, we had 5 different ways the data could be grouped under the classes. For 4 classes, you have 16 ways. And if you have 15 classes, there's over 1 billion ways you can group the classes together. So this is actually computationally infeasible. But if you want to consider set options is one versus rest, all you do is compare one class against the others. And in that case, you only have 16 groupings to compare, which is much more feasible for a large number of classes in your data set. And then finally, we have a generic S3 object predict, which provides a prediction method. We can return the probability of class membership, as well as just the estimated class labels as well. So let's apply this to the data set we have at hand. So I've applied it. Here's the application to the SRBCT data, which is inbuilt in our package. I can use the print function to have a look at the important things that come out. So it tells us all the information we already know. And it tells us the ranking of the features in terms of how discriminative they are. In this particular data set, we have 215 features not being the null, so there are some separation. And it tells us the likelihood of being under a particular petition. This is petition 8, so there's actually more output, but it wouldn't fit on the screen. And it shows you the different ways we can petition the data. But if I use the plot method and look at the first rank, it shows us how the split actually works. So in this particular case, we have groups 1 and 3 grouped against 2 and 4 for this particular feature. So it's pretty cool. So it's like it was a bit of a shift in the way I was thinking to think about they're not always just all together or all different. There are different ways we can group features together. And just showing you that this is not just a proof of concept, that it does actually work for prediction in this particular sense. So I'm not going to go into detail about all the methods that we have compared against, but here's our methods, multi-LDA, multi-QDA in the light purple. And we compare against many other machine learning methods, many other DA methods that are out there. We actually perform pretty well in terms of a cross-validation approach. Only beaten by the random forest and Lasso, but we have a more interpretable result in the random forest. And now onto my second method, which is generalized DA. So now we've dealt with looking at bioinformatics kind of data, wide data. This one does actually quite fit into the big data sense because this is just more of a generalized response type of algorithm. And we're shifting away from bioinformatics to image analysis data. So this study is an urban area of Florida, and I'm not too savvy with image data, but it's a type of picture captured from the sky. And they wanted to be able to classify different types of land cover in this data set. So we've got trying to classify if something's grass or tree or a car or asphalt or concrete and so on. Our data consists of 168 image segments to be classified with 147 features describing each image segment, such as area, brightness, and these are measured at different resolutions as well. When we do some investigation to the data, we see that the data is highly correlated, with a noticeable difference in correlation structure between the classes. So for example, we've got the car, we just subsetted the data based on car and had a look at their correlation structure, and the classes that are shadows, and we have a way different block correlation structure between the two classes. So if you do some investigation, you can see the car one is mainly correlated based on resolutions, and the shadow one is mainly correlated on feature type. And by the motivation of this talk, EDA shows that the data is definitely not normal, with a mixture of positive skew and count data. So I just got a snapshot here of the first 6 variables, and we have, if you look here, there's definitely here a mixture of positive skew and count. And our question is, how can we build a DA model to discriminate between segment type for the mixed response type? Now I'm going to warn you, this is the most mathsy project I've worked on to date, so I'm really going to be glossing over the details here, so please, if something doesn't make too much rigor, I've got a link to the actual mathematics online, but I'm trying to give you, it's an R conference, not a maths conference. So, we're going to fit a DA model as follows. We're going to use a type of model called a generalized linear latent variable model, which is a bit of a mouthful, but if you know anything about generalized linear mixed models, they're very similar. First, we're going to decide for each column what family describes that column. That's user defined, so you have to have a look and think, oh, that might be log normal or negative binomial and so on. And then we use this particular model called GLLVM to model distribution for each column, taking into account class information and capturing correlation between features. So how do we do this? So we have information tau I and beta naught j represent column and row intercepts. Class information is captured in xi with corresponding coefficients beta j. So we can think of our predictors of being the class. And now our correlation structure is going to be captured in ui and with corresponding coefficients lambda j, and the ui are latent variables. So thinking about the talk we had before, we have much fewer latent variables than we have features in our data set, so most often we have 2. And we're going to be using this unobserved term to try and capture how all these terms relate to each other. We can also model differing correlation structures by fitting different GLLVMs for different classes. So for example, I've got to split up my matrix by hypothetical class. So suppose I've got class 1, class 2, and class 3. They'll each have their own GLLVMs fit to them, which will each have their own latent variable structures. We can drop the class term because now all the information is captured in each separate GLLVM. And to predict, essentially for a new data point, we figure out under which class is our new data point most likely under for each GLLVM. For the model estimation component, we'll completely gloss over this. We use a Bayesian GLLVM, and it's quite computationally difficult, so we use a variational approximation method. In the optimization process, it's quite ugly, so we utilize the T&B package to perform automatic differentiation. So it's all implemented in a C++ backend, which is wicked fast, and it's quite fun for me to be able to use C++ in this. But these slides are online, and if you click here, I have a whole talk which goes into all the mathematics into this model fitting process. So very quickly, the syntax for this model, I apologize, is different to the previous model I had because the literature for this type of model is very different to the literature for the previous model I had. So now we have Y containing our matrix or data frame of responses. I do hope to streamline these two things one day. They will be not consistent with their literature, but they'll be consistent within the package. We have class containing factor class information. The number of LVs, latent variables, defaults to 2 in this particular case. The family is a vector of how you define what each column should be distributed as. So you have to do that user-wise. And we support Poisson, zero-inflated Poisson, negative binomial, binary, Gaussian, and log normal response types. And we're going to try to add some more in the future. You can specify whether the data has a common or different covariance structure. We actually have the row effect set to false by default. And you can also, for inference reasons, to see if your model's actually fitting well, have a look at the standard errors being calculated for the model parameters. It's set to false by default because it takes a while to fit these parameters. And we also have a predict method just like multiDA. When we apply this to this data set, the urban cover, we perform reasonably well in competitors, so random forest as well, and so does support vector machines. And we hope in the future to be able to do even better on different types of data sets. So thank you for listening to my talk. I have links. Oh no, here, everything's here. The hyperlinks are here. So this is all GitHub right now, not on CRAN just yet. I'm focusing on finishing my PhD before I try and do those CRAN checks. But right now you can go onto my GitHub and have a look at how everything works. Thank you.
Thank you. Questions for Sarah? Yeah, I have one question about, I think it was in second example, multiDA. Your example was about was a spatial example. I was wondering whether you could incorporate the spatial information as constraint maybe in your model.
Yeah, you probably could. I just haven't. I'm not an expert in spatial data analysis whatsoever, so I haven't actually tried to look into that component. But we're still trying to look at different ways that we can expand our model. You probably try and handle that as some sort of feature type, but I'm not a spatial data analysis expert anyway. We just found this data online. Yeah.
Thanks. More questions? Yes.
Can you tell us what was the toughest coding aspect of the work?
Oh, the toughest coding aspect for me, the TMB package is awesome. I highly recommend it. But of course, it uses we went to the AD talk yesterday. It uses a very similar backend, which is all in C++ and uses a CPP80 backend. And so you have to write your code in C++, which was a bit difficult for me because I've never used such a low-level language before. And then also integrating that into a package and getting everything to properly compile. There's a special folder structure you have to do. But it was quite rewarding after I'd done that step. And the package is very well documented, so it was very helpful and able to do that.